We'll now look at the algorithms for solving the maximum subsequence sum problem. The first algorithm is actually the simplest of all the algorithms. All we're going to do is just exhaust all possibilities. So we're going to look at all possible subsequences in our sequence and figure out which one is the largest of all these possible subsequences. Here is the code for this algorithm. So we actually have a method. We're bringing an array A. So we're going to say that A contains the sequence of our numbers. We have a max variable, which is initially 0. And notice we have a couple of for loops. So that should give you some hints on how long the running time is going to be for this algorithm. So the way we can think of this is we have I and j as our main loop control variables. And what's really going on inside the body of the second for loop is we're taking the sum of all the elements between I and j. That's what this third inner for loop is doing right here. So we're saying k goes from I all the way up to and including j, and we take the sum of all those elements. And we check to see, is this sum greater than our current maximum? And if so, we update max. And then we're going to move j over a little bit, and then we're going to take the sum of those sequence, and then we'll keep moving j until it gets all the way to the end. And then what happens is we do the next iteration of our first for loop, so we're going to move I over one spot, and we're going to take the sum of everything between I and j, and keep moving j to get all those different subsequences. And we just keep repeating this until we get to the end of the array. So this algorithm looks at all combinations of sequences, and we end up storing the current maximum value. The way we do this is we just simply look at all the subsequences that are between I and j. So we'll keep moving j down and take the sum of that subsequence, and then we're going to increment I, and we just keep repeating this. This algorithm is the one that takes O of n cubed time. So why is that the case? Why does this algorithm take O of n cubed time? Well, the first for loop has O of n iterations because I is going to start the beginning and goes all the way to the end of the array. The second for loop, the j part, that also has O of n iterations. And then what about the third for loop that we mentioned, the one where we have k goes from I to j? Well, that actually has j minus 1 plus 1 iterations. Well, I can't really say O of j, but since j can increment n times, we actually find that this third loop technically has O of n iterations. And then since all of these loops are nested, we just multiply the sizes of all three of these loops, and everything else in there does take constant time, the other statements. So this turns out to be O of n cubed time. Now, technically, this algorithm is actually theta of n cubed. I should mention that, but we're not going to worry about proving or showing that this is also omega of n cubed time. But right now, we can just say that it does take n cubed time. Since the last algorithm does take O of n cubed time, and we know that that doesn't really help us when n becomes really large, we need to improve the running time. And in this case, we can actually do that by removing a for loop. Now, you might think, can we just do that with regular algorithms? If we have a bunch of for loops, can we just take out a for loop? No, normally we can't do this. But in this particular case, we find that our algorithm has a lot of unnecessary computations. We find that we really don't need to get every single subsequence in our sequence to actually figure out what the maximum sum is. And we find that the improvement comes from the following observation. So we're going to use the following formula. So if we're trying to get the sum of ak, where k goes from 1 to j, that's technically the same thing as taking the sum of ak, where k goes from 1 to j minus 1. We take that sum, and then we add aj afterwards. Here's the code for the second algorithm. So notice we have our first for loop here, right here, if I can draw right there. And then here is our second for loop, our j loop. And notice that the k loop is missing, because what we're doing here is for each iteration of the first for loop, we're going to reinitialize our sum to 0. And then we're going to keep incrementing j. And as we compute the sum as we go from I to j, we stop and ask, is this current sum greater than the max? And if so, we update. And then we would move on to the next one. and then we move on to the next one and so forth. So we're still kind of getting all the combinations. We're just doing the math a little bit differently, because when we get to the end of j, we would then increment I by 1 and move to the next spot, and then we would reset j, and then as we move j, we would take the sum again as we go, but we're checking each sum instead of having to do like this entire computing the entire sum between I and j and then checking. We just compute as we increment j. So what we have here is we now have 2 for loops instead of 3 for loops. And what this means is this algorithm takes O of n squared time instead of O of n cubed time.